Hello, my name is Darren Thomas and I'm the Director of Educational Research Techniques. In this video, we're going to talk about summation notation and partial sums. So let's go ahead and get started. Now, we've been talking about sequences for a while, so why don't we start by looking at a very simple sequence, and then I'll try to show you where summation notation and partial sums comes in from that. Imagine I have, the general term A of n equals n. So if I were to make my table, it would look something like this. I would have A sub n here and then n here. And so 1 would be 1, 2 would be 2, 3 would be 3, 4 would be 4. I hope that makes sense by now. If not, you need to check the earlier videos. So if I wanted to try to write out what's going on, because essentially what's happening that summation notation is where you take a sequence and you add up all the numbers. So let me just show you manually how this works. So let's say I have A1 plus A2 plus A3 plus A4. Now A1, 2, 3, 4 is right here, so it'll be essentially 1 plus 2 plus 3 plus 4, and that will equal our answer of 10. That's our answer. Now there is a shortcut way to write this information without having to do it all explicitly, and that is where summation notation comes in. So to make this as simple as possible, here is the basic structure for summation notation. Excuse me. So we have our value here. We have the capital letter sigma from the Greek alphabet. That's the first thing you got to know. And then below the sigma sign here, we have the letter I. Normally it's an I, and often it'll equal 1, but not necessarily. I will explain what that means in a second. Above the summation, you have the number 4 here. Now, again, I'll tell you why in a second. Just be patient. And then off to the right, you have whatever is going on here. So this is what's happening. So let me explain this piece by piece. So the capital sigma here, that's our middle term, this Greek letter right here. That just means sum. That's what it's telling us. I tells you where to begin at. So we're going to begin at the number 1 because that's our first number right here. Now the 4 tells you where to stop at. So we're going to go from 4 all the way up, from 1 all the way up to 4 because that's our last term right here. So from 1 to 4, and then this guy tells you what to do. This guy tells you what to do with the number. So because it's next to the summation, it means add them up. So in other words, start at row number 1 or with the number 1, go to number 4 and add up each term. And so we already did this previously when we did it by hand up here at the top. So this information right here is capturing the same information that is found right here. And so if we follow this summation notation and we look at our little table over here, we'll also get the answer 10. We'll go through the same A1, A2, A3, A4, 1 plus 2 plus 3 plus 4, and we'll get the 10. But this is a shortcut way of doing it. Now the last thing I want to explain before I go to the examples is that this 10 here, which is the answer when we sum everything up, it is also called the partial sum. That is the answer when you're dealing with summation notation. Now having said that, let's look at a few practical examples here. So here's what we're going to do. Here's our first example. So imagine I have the following. I have summation here. I'm going to do an I equals 1. Ooh, I equals 1. Top number is 4, and then 3i. So now notice how we're not using the n because we're using a slightly different notation system. However, I need to mention that sometimes they use the n instead of an I here in some places. It all depends. But let's get back to our point. So this is what we're doing. We're going to start with the number 1, go to number 4, and we're going to add together each term 3 times I. So this is what it will look like if we wrote it out manually. It'll be 1 times 3 plus 2 times 3 plus 3 times 3 plus 4 times 3. That's essentially what it is. Okay, so then we got 3 here, 6, 9, and 12. And so all this will add up to the partial sum, if you will, would be 30. That's how this works. Now, if I want to be really strict, I should have wrote 3i and 3 times 2, 3 times, and that one doesn't matter, and 3 times 4, because that's the order that we have our terms in. But we got the same answer, so it's okay. Let's do one more, at least 2 more examples here. So here's our next one. Again, hopefully you're getting the pattern and you're realizing this is not that complicated. but just in case you're not comfortable, let's do another one. So that's our Greek symbol, sigma. Now this time the example uses K. So we start with K. Like I said, this letter can change. We start at 0 and we go to 3, and this is what we're going to do. We're going to do 2K. 2, oh boy, that's really kind of big there. 2K factorial, like that. We learned about factorial notation last time. So to go through this example, here's what we would get. So we're always going to have 2 as the numerator. And so for our first example, we're going to have 0 factorial like this, plus 2 over 1 factorial, plus 2 over 2 factorial, plus 2 over 3 factorial. And so 0 factorial, that always equals 1. You could just talk to mathematicians about why. So 2 over 1 plus, this is going to be 2 over 2 times 1, which is essentially going to be 1, plus 2 over, oh, whoa, sorry about that. This is going to be 2 over 1 as well, plus, sorry about that, 2 over 2 times 1, plus 2 over 3 times 2 times 1. So then we got 2, well, let me give you a different color here. We got 2 plus 2 plus, let's see here, that's going to be 1. And then this is going to be 2 over 6 plus 1 over 3, basically. And so our answer, I'm a little out of space here, so I got to move up the top here. Our answer is going to be, let's see here, 2. Oh, that's not 2. That should be 2, 2, 2. Oh, I forgot to put the 1. Put the 1 right here. Okay, so our answer should be 5 1/3, if that's what you want to see it as, or you can also write it as 16 over 3. Either one. But that's the answer. Let's do one last one and we'll conclude this video. So now with this one's going to be different because we're going to start with the actual sequence and then we're going to try to create the summation notation. So watch carefully. It's a little bit trickier. It's kind of like thinking backwards. 1/2 plus 1/4 plus, let's see here, 1 over 8 plus 1 over 16. Looks tricky, but let's see if we can piece this together as simply as possible. First of all, I know I need my summation notation like this. Now, one thing is very clear. If I count the number of terms, I can get the top number right here. So 1, 2, 3, there's 4 of them. So I know the top number is 4. That's not that hard. I also know that it's going to be, you know, I can call this I or N or K or whatever, but I know it's going to be something. So I'm pretty sure it's going to start with 1. So I'm going to put that for now and see what happens. N equals 1. Now I need to figure this out. All right, now in every single example, the numerator is always 1. So it's going to be something with a fraction. I know that. And so I'm just going to put a 1 on top, but I'm not quite sure what the bottom number is yet. Now I have to think, what can I do to get from 2, 4, 8, and 16? Well, they're all factors of 2, so it's probably something with exponents maybe. Because, you know, 2 to 4 to 8 to 16. For example, 2 to the 1 will give me 2. 2 squared will give me 4. 2 to the 3rd power will give me 8. And 2 to the 4th will give me 16. So I'm thinking, and this is probably correct, that it's definitely going to be a 2 and it's going to be raised to the n. And so you can see through some reasoning and stuff that I was able to determine the answer. And so you can check this for yourself. Like I just did out loud. This is, you know, this is 2 to the 1st power, this is 2 to the 2nd power, this is 2 to the 3rd power, this is 2 to the 4th power. You can just see the pattern. I don't know if there's any kind of mathematical way to prove it, just using intuition is kind of how I got the answer. And you can see that, you know, we were able to, you know, pull the summation notation to figure out what the answer is. Now, one thing we didn't do is we didn't get the partial sum. In other words, we never added up all these different fractions here. We started with the sequence, and then we were able to derive the summation notation from that. But if you want, you can find out what the partial sum is on your own time. So let me go back and kind of review what we talked about in this video and then wrap things up. So in this video, we were introduced to summation notation, a very practical way to summarize the situation in which you have to add up the terms of a sequence. And so we started with a very basic general term here, general sequence term, and from there we were able to derive the pattern for how to create the summation notation. The sigma is the letter that we use that means add. The term below the sigma just tells you what number to start with. The term above it tells you where to stop. And then this tells you exactly what to do each time when you're adding. That's kind of how it works. And then we have some examples. So here, we start at 1, we go to 4, and we multiply by 3. And you can see the example right here, and then we added it together, and we got 30. For the next example, this one we started with, we had the factorial, we started at 0, we go to 3, and it was always 2 over k factorial. Now notice how the letter was different. What letter you use, it really depends on the situation. Sometimes, mostly I, often N, maybe K, whatever, it doesn't really matter. But again, we go through the same process. Of course, in this example, you had to be familiar with factorial notation, which was something we discussed earlier. And you can see that we were able to get the answer 5 1/3 or 16 over 3. And then for the last one, what we did here was that instead of starting with the summation notation, we started with the sequence, and we had to extract the actual summation notation from the sequence. And so we chose to use the letter N this time. Nothing special about that. We could have changed it to something else in case that confuses you. And you can see that here by raising the denominator to whatever power of N, you're able to get the answer. So I hope that this makes sense for you and that you're able to understand kind of what was going on here. My name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.